Hello, is it visible na po, ma'am?
Yeah, but can you make it larger, like bigger?
Wait lang po. Okay na po.
Yeah, nag-ano lang siya, yung parang extended na form. Nevertheless, okay lang naman.
Okay, so good afternoon, ma'am. Good afternoon, classmates. So I'll be reporting about the pharmacokinetic model and parameters. So these are the topics to be discussed. First, the 1-2 compartment and the non-compartment pharmacokinetic. And my partner, Sir Steve Abesha, will be the one to discuss the latter part po. So to start, compartment model is a mathematical representation of the body or an area of the body created to study physiologic or pharmacokinetic characteristics. It can stimulate all of the biological processes involved in the kinetic behavior of a drug after it has been introduced into the body, leading to a better understanding of its pharmacodynamic effects. So there are two. I'll be discussing the 1-compartment model and the 2-compartment model. So for the 1-compartment, so it is a simplest compartment pharmacokinetic model, as the name suggests. It is a model considers the whole organism as a single compartment where the drug distributes homogeneously and instantaneously. An extreme simplification that leads to a very simple mathematical description. So the assumption of the instantaneous and homogeneous distribution also implies that the apparent volume of distribution, or VD, will be constant. Another second and very important assumption of the model is that the drug elimination within the compartment occurs the following. First, order kinetics. Depending on the modeled therapeutic scenario, drug absorption will be assumed to be instantaneous or IV bolus, or to follow zero or first order kinetics. The 2-compartment model, it describes the evolution of a drug level in the organism by depicting the body as 2 pharmacokinetic compartments. So it also referred to as the compartment 1 and compartment 2. So once a given drug amount reaches one of these compartments, it distributes throughout it immediately and homogeneously. However, the movement from one compartment to the other is not instantaneous but follows first order kinetics.
Parang walang voice, ma'am.
Sorry? Ay, ano yun?
Asan ako nag-end, ma'am?
Ayan, dito. Nawala yung yung audio.
Asan po ako nag-end dito sa when to use non-compartment analysis?
Yeah.
Okay, sige po. So, it is used, the advantages includes exploring the pharmacokinetic variability due to intrinsic factors and extrinsic factors such as the age, sex, race, renal impairment, hepatic impairment, and also informing dosage adjustments based upon these factors. So how it is being performed. So it relies on observed drug concentration measurements over time in a relevant accessible matrix. So these measurements are provided to the pharmacokinetics by a bioanalytical lab where blood or plasma samples from study subjects are analyzed using sensitive detection techniques. So these are the common parameters used in non-compartmental analysis: the maximum concentration or the Cmax, and the time of the maximum concentration or the Tmax. Also, the area under curve, volume of distribution, systematic clearance, and terminal half-life. So I'll give the floor to Sir Steve Abesha.
Hello, good morning sa tanan. So let me just prepare first for the non-compartmental PK. Let me just navigate first sa Zoom kay dili ko kabalo. This one po mga ma'am, makita na sa tanan. Hello
White,
po.
white pa lang siya. Or white.
So makita na ang white.
Yeah,
So let me start first for all the PK parameters. T1/2 or your half-life. This refers to the time required for plasma concentration of a drug to decrease by 50%. It is dependent on the elimination rate constant, your key E, which is related to VD, your volume of distribution and clearance. In other words, after one half-life, the concentration of the drug in the body will be half of the starting dose. Here you can see a familiar graph which follows the first order kinetics of elimination, which is a majority of the drugs follow from 100%. So guessing from it would be a IV drug from 100% down to 50% from its half-life in its first half-life phase, and down to 25 and 12.5 and succeeding. There are 5 phases of half-lives, which ako pag-discuss next sa mga uban nga terms. And to some others, disappointment, and to some others, sigh of relief, I have only prepared this formula. Just a small and basic formula in which masabtan na sa akong few brain cells, so I apologize for that. And I prepared some problems which are still basic and di na kayo kailangan o mga scientific calculators. With the formula above, you are tasked to find half-life of a drug having 220 liters of VD and a clearance of 50 liters per hour. So with that, just basic math, and let's just replace it. 220 times 0.693 divided by 50 liters per hour. The liters will be eliminated and the remaining would be R. So the R would be half-life. And by that, we would get a 3-hour half-life. So in this graph, for example, the 100 in its first half-life, after 3 hours, ay apply sa mamanisan of 50%. So basically, kana lang akong ma-discuss. So the very basics lang sa for this one. Let's just proceed with LD or your loading dose. An initial higher dose of a drug that may be given at the beginning of a course of treatment before dropping down to a lower maintenance dose. It is the dose required to immediately achieve plasma concentration equivalent but not identical to steady state concentration. A loading dose rapidly achieves the peak concentration necessary to compete with clearance so that the desired effect is achieved and maintained sooner. So this one, from 0 immediately to 100. So we could say this is an oral drug having a loading dose from 0 up to 100 immediately. And after that, after reaching its first half-life, then we would do our maintaining doses for that one. With the formula of volume distribution times the concentration over the bioavailability. We have a question here. Give the loading dose of a drug having 50 liters of VD and a clearance of, rather the concentration, that would be concentration of 5 milligram per liter. And with that, makancel out na to ang liters. And ang F na to diri would be, let's disregard the graph. The F would be, let's say 100% if it's given in intravenous, so 1. So it would be 50 times 5. And with my very basic math, with 50 times 5 would be 250. That would be 250 milligram, our loading dose. And proceed to the next. Dosing intervals. It is a repeated time period of dosing when at steady rate, concentrations will rise and fall according to a repeating pattern as long as we continue to administer the drug at the same dose level and the same time period between doses. This is a typical example of our dosing intervals with different doses and different time doses. Time interval for doses. TID dosing of 60 milligram every 8 hours. The other one in B would be 90 milligram of every 12 hours and every 24 hours. As you can see, mas nagkataas ang concentration and dose would be mas taas po ang dosing interval. Next, our CCS, or steady state concentration. It occurs when the amount of a drug being absorbed is the same amount that's being cleared from the body when the drug is given continuously or repeatedly. CSS is the time during which the concentration of the drug in the body stays consistent. The importance of this is in knowing the rate of the drug that comes in and the rate that it goes out. Usually CSS is reached within 4 to 5 half-lives, just like kanina. From the very first, from the half-life, we would reach our steady state concentration after the 5th half-life. Drugs with short half-life reach steady state rapidly, while long half-life takes days to weeks to reach its steady state concentration. We have your KE, as everyone is familiar with. KE is the elimination rate constant, a value used to describe the rate at which a drug is removed from human system. It is the concentration of a drug in a system after infinitely small change in time. The elimination rate constant represents the fraction of drug eliminated per unit of time. This follows in first order kinetics, which elimination rate is proportional to the dose. Here we have the K 0.693 over T1/2. So with this basic example, katong first example, we have our drug with a half-life of 3 hours. So at the constant rate elimination, let's try and solve it with 0.693 divided by 3 from atong first problem kanina. The answer would be 0.231. That would be the elimination rate constant of which the drug is eliminated from the body. Then we have your clearance. Clearance is equal to the rate at which a drug is removed from the plasma divided by the concentration of that drug in the plasma. So basically, kani siya nga formula, clearance elimination rate over concentration. Para sa mga, just to clear it out, the difference between the clearance and elimination. The concept of elimination and the concept of clearance, the terms are not synonymous. even though they sound as if they might be interchangeable. Some authors in some books make a firm distinction between the term clearance and the term elimination, even though it is not always explored to some satisfactory degree. In some book called Applied Pharmaceutics and Pharmacokinetics, elimination is defined as irreversible removal of the drug from the body, and clearance as volume of fluid cleared of drug per unit time. Most textbooks refer to the rate of elimination as the amount of substance cleared from the blood, whereas clearance seems to always be the volume of blood cleared of substance. The fundamental concept is that the total body clearance is the sum of all individual organ clearances. And as we have known, there are several different organ-specific clearance ng mga concepts. We have system clearance, we have renal clearance, metabolic clearance, hepatic, and intrinsic unbound clearances. And we have the last, AUC, area under curve, in which it is the area under the plasma drug concentration time curve that reflects the actual body exposure to the drug after administration of a dose of the drug. Here again is a familiar graph of our AUC. Whatever the curve that masakop sa curve, that is our AUC. And AUC is determined through our Cmax and our Tmax, concentration maximum and our time maximum. There we can see our toxic concentration or minimum effective concentration in our therapeutic range. And that's basically just it for this quite basic definition and some very simple way of computation of our biopharmaceutics, even though it does not really targeted what we really need to learn from this one, but it is a refresher for some of us. So thank you, classmates, and thank you, ma'am.
Okay, thank you for that, ma'am and sir. Again, this will just be a review now since we are actually done with these concepts during our undergraduate years. But let me just give supplementary information lang about this. Wait lang. So, hindi na ko siya in-open. Okay. Okay. So here it is. So once again, let's talk briefly about our pharmacokinetic compartments. Not sure. Okay. Ano siya? So again, when you say pharmacokinetic compartment, this is the model that we use just for us to describe the spaces in our body wherein after drug administration, dun pupunta yung drug. So again, this is just our mathematical representation of that. Now, we have two types for our compartments. We have one compartment and the two compartment. Actually, we also have multi-compartment, no? But our reporter a while ago discussed, first we have the one compartment. If we're going to illustrate that, example, we have this drug, we have 1 gram of the drug. And then if we are going to use this concept, it means after administration, the whole body, okay, will have a homogeneous amount of drug instantly. Okay, again, instantly kasi one compartment lang. We will treat the whole body as one compartment only, and that after administration, all parts of the body will have an instant amount, homogeneous amount of the drug. However, we are going to look at the two compartment model for our drug absorption and distribution. we will have like this. We have the central compartment and also the peripheral one. So that makes it two compartment model wherein after drug administration, we will have first the central compartment receiving the drug, and then it will be distributed to the peripheral compartment at a certain rate. So after that, there will be exchanges of drugs between peripheral and the central compartment until there will be an equilibrium, okay? Meaning both compartments will have a homogeneous amount of the drug after. So why do we need to know these concepts? This will help us actually study the pharmacokinetic profile of the drug, and it will help us class determine kung saang part na ng ating body nandoon yung drug natin and gaano siya katagal magsistay and yung elimination. At mapipredict natin, we are going to study the two types of our compartment. So this one is another illustration here. So before administration, so definitely there is no drug all over the body. However, after administration for one compartment model, there will be homogeneous amount of drug all over the body. There is no barrier. The movement of the drug is constant. Now, this is naman for the two compartment model, wherein after administration, we have the so-called central compartment. And then we are going to wait before class the drug can be distributed all over the body. So we have to consider here perfusion rate of the drug and yung mga barriers that need to be crossed for the drug to be distributed to other parts of the body or the so-called peripheral compartment. So depending on the compartments or the models that we are going to use, meron tayong mga kino-compute example, the elimination rate constant. So definitely for one compartment model, we only have one elimination rate constant since we only have we treat the body as one only. So after administration, we only have the distribution, then after elimination na kaagad. So again, the drug is eliminated at a certain rate, pero we only have one elimination constant for that. However, that is not true for our two compartment model since the drug will be distributed from the central to the peripheral. So if we are going to compute for the elimination rate constant of the drug, we need to consider the movement of the drug from the central to the peripheral and the vice versa. Meaning from the peripheral, it can go back to the central compartment, remember, until the amount of drug will be homogeneous. And then after that, we have the so-called K10, which is actually the elimination rate constant of the drug from the central compartment. Okay, that is two outside of the body. Okay, so ayan, this is just again for us to be refreshed with our concepts in pharmacokinetics class. We have to know kung anong compartment model ang susundin natin in the study of a specific drug, in the study of its pharmacokinetic profile. Now, these are the so-called pharmacokinetic parameters na diniscuss ni Sir a while ago. We have here the following. So, we can illustrate it using the graph. We have this graph, time versus concentration. So definitely at 0 time, there is no drug yet, but after administration, you will see the graph going up until it reaches the Cmax. The Cmax is our peak plasma concentration, the maximum amount or the maximum concentration that is achieved in the body, after drug administration. Okay, and that includes class the computation or measurement of the time of absorption or the rate of absorption, and at the same time, the rate of drug elimination. So after reaching the Cmax, we will have the half-life. It's the amount of drug it's the time wherein 50% of the drug is eliminated and 50% is still in the body until it reaches the C minimum. Ito na yung talagang na-eliminate na yung drug from our body. So the time wherein we reach the maximum, the peak plasma concentration is the Tmax. Okay, that's the Tmax. Now starting from the half-life, again, it's the time wherein half of the concentration remains in the body and half of that is being eliminated. Okay, so what are the other parameters that we need to consider for us to know the half-life of the drug? We have to know the K. K is syempre the elimination rate constant. So ito yung present ni Sir a while ago. We have here T1 half is equal to 0.693 over K. You can use that in the computation if the K is known or the elimination rate constant is known. However, if ever the K is not given, then we may use this formula. So T1 half is equal to 0.693 times V, which is the volume of distribution. We'll talk about that in a while, divided by its clearance. So pwede yung dalawang yan gamitin to determine the half-life. Okay, so why do we need to know the half-life of the drug? Syempre, for us to know the time or to estimate the time wherein the drug is eliminated in the body, and at the same time for us to know, we can actually know the steady state, the time we reach the steady state concentration in our body, and thus the dosage interval. Syempre, if we know the elimination half-life, we can estimate when are we going to give the next dose. Okay? So, ito yung estimation natin. Half-life of the drug determines time to eliminate drug from the body. So, definitely, one half-life means 50% of the drug is being eliminated. So, after another half-life, so 2 times the half-life, that means 75% of the drug is being eliminated. So 25% remains and so on. Meaning it will take 7 half-lives for us to eliminate 99, almost 100% of the drug in the body. Okay, so the longer the half-life, the longer the time to elimination. And we can determine after that when are we going to give the next dose and for us to maintain the steady state concentration. However, we have to consider if the patient has renal problem, this one can prolong the half-life of the drug. Okay, so that's the first pharmacokinetic, sorry for the spelling typo, huh? Now, after the half-life, we have here the steady state concentration. It's the plateau actually. If we are going to make the graph of the concentration versus the time, especially the half-lives, we are going to see here the time wherein there is a plateau, which means we are going to reach the steady state concentration. Okay. Sige. Let me, I'm gonna skip some slides here. Okay. Okay. So ito, since sabi ko kanina, half-life class determines the steady state concentration. If baliktarin natin yung graph, no? So, di ba, during the first half-life, 50% of the drug is being eliminated. And then we have here another one, kasi rate of input is equal to rate of output. Ito, after the second half-life of the drug, you have here 75% of the steady state kung babalik na rin natin. Pero actually, after five half-lives of the drug, that's the time wherein we reach the steady state concentration. Okay? So the shorter the half-life of the drug, the shorter we can also achieve the steady state concentration. This the concentration in our bloodstream sa drug na in-administer. Now, ito, we have here example, 2 new antibiotics are marketed by pharmaceutical manufacturer. Reading the package insert, you find this information. So we have here the dose, the steady state concentration of the first antibiotic, that's uracilin, and the betamycin. That's the second one. So if you are going to administer 100 milligram of the drug, you will reach the steady state concentration. If you reach this one, 15 milligrams per ml, and so on ito. Okay, so ang question, what type of pharmacokinetics do each of these drugs follow? Dito papasok yung study of the first order kinetics and the zero order kinetics. So do not forget, just a little review since tapos naman na tayo nito. Syempre, if we have like yung uniform amount of drug being eliminated, you have constant amount of drug being eliminated at constant time also, that is zero order kinetics. However, if the elimination is dependent on the amount of drug or the concentration of drug left in the body, that is first order kinetics. Okay? So most likely the curacilin follows a zero. Yes?
5,000 per month. Pero parang tumaas na yung tuition ngayon?
Oh, wait lang
16,000?
ha. May nagsasalita ba? May nag-ask ng question? Wala? Or na-on lang ang mic? So, wala, no? Nasaan na tayo? Wait. Let's go back. Okay. So most likely, curacilin follows zero order kinetics. So as you can see, yung steady state concentration niya din, kasi kung balik rin natin, you'll have the half-life, no? The steady state concentration follows class A constant increase if you increase the dose. And that is the reverse, the other way around for the betamycin. Kasi you get to see here, most likely it will follow a first order kinetics. Okay, so you will have not really a constant steady state concentration as you increase the dose. Okay, now aside from that, we have this another parameter, the drug clearance. So from the name itself, drug clearance, it's the amount of drug, especially the volume of the blood, the plasma, or the serum being cleared by the drug for a period of time. So in computing for the clearance, we're going to use this formula. Clearance is equal to K over the concentration. So K is the elimination rate in milligrams per hour, and the concentration in milligrams per liter. Okay, or if that is not the given, we don't have the elimination rate or the concentration, yung wala, we can use the formula. Clearance is equal to the volume of distribution times the elimination rate constant. Okay? So, in computing for the KE, pwede natin syempre i-derive yung formula natin. Clearance is divided by the volume of distribution. So, what do you mean by volume of distribution? This is not actually a physiological parameter. This is just yung hypothetical na parameter wherein we estimate or we approximate the volume of the body fluid wherein the drug is being distributed. So sa volume of distribution, we also do computation, no? Sa undergrad, we do the manual computation, but definitely if you're going to work as a pharmacokineticist, meron tayong mga software for this. So volume of distribution is just the dose of the drug, most likely in milligrams, divided by the plasma concentration. So again, this is the body fluid. So it can be this one, the plasma, and the interstitial fluid, and the intracellular fluid. Okay? So most likely if we get if we get a 4 liter na volume of distribution, the drug is still in the plasma. But if it is 10 liters, approximately 10 liters, the drugs are being distributed in the interstitial fluid. And if masyadong malaki, then the drug is in the intracellular fluid. Okay, so that is just the distribution of the drug to our body fluids. The body fluids are being treated as a compartment. Okay, so ganito. If the drug remains in the blood, meaning if we get to have a volume of distribution, example 4 liters, nasa plasma yung drug. Wait lang, bakit siya nag-next? Ayan, if we have low VD, so example, in the plasma pa yung ating drug, it means that there is decreased tissue binding. So, meron tayong hindrance in the distribution of the drug in the tissues. Remember, after the absorption, the drug is in the blood and we need to distribute that for the drug to reach the target site. Okay? However, if the drug remains in the blood, that means there is decreased tissue binding or the drug is bound to our plasma protein. So that's one thing that we need to consider, especially for dosing intervals natin, yung high plasma protein binding kasi it will hamper drug distribution. And then, if we get to have a high volume of distribution, it means the drug has penetrated the tissues already. There is increased tissue binding and that the drug does not really bind so much with the plasma proteins. Okay, so how do we again, wait lang, ito. Ayan, we have here scenarios, examples of drugs. We have dose is 100 milligrams. And then you have here a concentration, blood plasma concentration of 100 milligrams per liter. So again, we can compute the volume of distribution using this formula, dose over plasma concentration. So example, 100 milligrams ito, no? This is our dose administered to the patient. And after a certain time, nag-measure ng blood concentration or plasma concentration, and that's 100 milligrams per liter. And we have here a volume of distribution na 1 liter. So that is considered a low volume of distribution, which means the drug is still in the plasma and there is a high possibility of the drug having merong mataas na tissue or blood protein binding or plasma protein binding. Now, ito yung another scenario of the drug. We administer the same dose, 100 milligrams, but the measured plasma concentration is just 1 milligram per liter. If you're going to compute for the volume of distribution, we get a high one here, that's 100 liter. And that means, when again, if we have high volume of distribution, that means the drug has already penetrated into the tissues. A little amount of drug has remained in the blood. Okay, so meaning mababa yung plasma protein binding natin dito. The drug again has penetrated the tissues and most likely we get to have the target site. The drug reaching the target site. I'll skip some of the slides. Okay, so again, our volume of distribution is represented in liters. So we may actually multiply this one in the weight of our patients. So we can see the pharmacokinetic profile of the drug example sa mga inserts, no? Sa mga drug inserts or sa mga references. And if we want to know the volume of distribution, we can just multiply this one, the liter per kilogram na ang tawag dyan, yung concentration of the drug to the weight of the patient. We will get the volume of distribution. Okay? So, we can approximate here kung gaano ba kataas ang protein binding ng drug natin and gaano siya kabilis mag-penetrate ng tissue. So, here are the examples. So, si gentamicin, we have a volume of distribution, we have 0.25 liters per kilogram. Therefore, if the patient weighs 60 kilograms, we will have here 15 liters na VD na volume. And this is actually medyo mababa compared to the digoxin, which is 420 liters. So most likely digoxin is highly, it can highly penetrate tissues. Mas madaling maka-reach sa target organs. Okay, so that's how we use the liters per kilogram na volume of distribution given per drug. Para alam din natin kung highly maka-penetrate siya or hindi. Madali siyang maka-reach sa target sites. Now we have also the loading dose or our priming dose. Okay, so this is our initial dose or first dose to be given to the patient. And this, if we're going to determine this one, this will also help us determine our steady state concentration. Gano'n natin kabilis ma-achieve yung steady state concentration natin. Ayun mo na mag-move. Nangyari here. What happened? So this is how we get our loading dose. We need here our volume of distribution and at the same time, the target concentration. Okay, so again, why do we need to know our loading dose? For us to know our steady state concentration also. And malalaman natin kung paano ba natin i-administer yung ating drug. So ito yung mga kailangan natin ha. I'll be giving you example. Pero ba't ang tagal mag-move? Kita nyo sa screen. The loading dose pa rin. Ay, mag-move ng aking slide. Okay. Ito lang ang laptop ko.